Unit 7, Basic Circular Motion. In order to get this unit going, we're just going to make a car go in a circle. Alright, there's a little car going in a circle. Overhead view of it, of course. And let's talk about that radius and the fact that that radius gives us a circumference. Circumference equals 2 pi r. Very good. There's three main properties of an object experiencing circular motion that we want to keep track of. The first one is tangential velocity. That is to say, the velocity with which it makes its way, around the circle. Tangential velocity is equal to circumference over period, period being the time required to make one complete turn of the circle, if we're able to measure that. And tangential velocity is given as a vector that does this, which is, of course, tangential to the circle that has been generated. The next value that we want to look at is centripetal acceleration. Centripetal acceleration is equal to the tangential velocity squared divided by r. Centripetal acceleration is always directed towards the center of the circle. Centripetal acceleration directed towards the center of the circle. And then finally, we have our centripetal force. I guess we should put it in black. Centripetal force. Centripetal force is equal to mass times the centripetal acceleration, but we really don't use that form of the formula too often. More often than not in our classroom, we probably unpack the centripetal acceleration and gives us centripetal force is equal to tangential velocity squared divided by r. Centripetal force also directed towards the center of the circle, as shown here from that force vector directed towards the center of the circle. And in all honesty, a bunch of the rest of the unit is just applying these basic topics in a variety of situations. Let's go attack one right now. The centripetal force apparatus refers to an object which we'll deal with in class, and we'll play with this in lab, in which we have a hollow tube, and we have a string attached to it, and attached to both ends of the string are masses. Let's go ahead and label our masses real quick. Mass number 1 and mass number 2. And it's a neat phenomenon in which we swing mass number 2 in a circle, any circular pathway, such that it generates a centripetal force, and that centripetal force is such that it overcomes the force of gravity of object number 1, and it is therefore suspended in the air by that centripetal force, and it's Newton's third law reaction pair force of tension that holds that object in place. We'll use this apparatus to calculate for the centripetal force in lab and make sure that it's roughly equal to that force of gravity. Measuring the radius of this string in order to calculate the centripetal force, measuring the circumference of the pathway such that you can calculate the tangential velocity, and all those practicing topics we'll get to explore. So that's centripetal force apparatus. The next topic that we do is the flying pig lab. In this lab, you suspend an object. In our case, it'll be a pig, and you'll suspend it from an elevated position, and then you'll cause it to go around in circles while it's still being held at its elevated position. Once it goes around in circles, it'll be generating this conical pathway that's indicative of, the flying pig lab. That conical pathway is important because it gives you 3 force vectors and a reference angle. Force given here is force of tension of the string holding that pig in place. Force given here is the force centripetal, directed towards the center of the circle. Force given here is the force of gravity of the pig. And that's one of those unique times when we get to grab a force vector and superimpose it somewhere else to generate a right triangle. The force of gravity originated here, but we were able to move it to make this cool right triangle that we can use, and therefore find ourselves an angle and use that to make any sort of trigonometric adjustments necessary in order to solve for, centripetal force or whatnot. That's the flying pig lab. The next specific topic addresses cars making a turn. Let's say that we're staring, we're behind the car and we're staring at it like so, and maybe the car is trying to make a turn. Now this is an unbanked roadway. We don't want to get into banked roadways right now and deal with free body diagrams on inclined planes. Let's suppose that a car is attempting to make a turn. In order to solve that, we'll build a quick free body diagram, which should be pretty painless. You got your force of gravity, you got your normal force since you're on an unbanked turn, those two vectors being equal to each other, and you have two horizontal forces going on. You have your force of friction that actually pushes out, and of course you have, since we're dealing with circles and circular motion, your force centripetal, directed inward towards the center of the circle. And a lot of these questions are phrased like, what minimum velocity must the car maintain to not skid along the pathway? Or how wide must we make the turn? Or what must be the coefficient of friction between the tires and the roadway surface in order to, just barely make the turn or not skid or that sort of a thing? In order to do that, we basically say, hey, to just complete the turn, your centripetal force must be essentially equal to your force of friction. Because if those two force vectors are equal to one another, you don't skid. Now, once the centripetal force overcomes the force of friction and becomes bigger, now you are skidding and you've lost control of your vehicle. It really won't be that the force of friction will ever be greater than the centripetal force, because you remember how forces of friction work. It's really impossible for it to be bigger. So as long as the force of friction is matching your centripetal force, you're all good. Let's unpack that real quick. Force centripetal is equal to mvt squared divided by r. Force of friction is equal to unpacked force normal, which in this case is just mg, times our coefficient of friction. All right, once we get to here, we notice that there's m's on both sides of those equations. So the mass of the car does not matter as long as we're trying to make our turn. What does matter is our tangential velocity, r, acceleration due to gravity, which is constant. We're always going to be doing this on Earth. And then the coefficient of friction between the tires and the roadway surface. Finally, we have our loop-to-loop questions for circular motion. Loop-to-loop problems usually involve, hey, we have a cart, and what minimum velocity must it be going in order to complete the loop-to-loop? Or those sorts of questions are what we ask here. In order to answer that, let's assume that we're just barely going to make it. Well, to figure out really what's going on, we do sadly have to build a couple free body diagrams. No! Well, at the top of the loop, we basically have three forces acting on us that we want to keep track of. You got your gravity, you got your centripetal force directed towards the center of the circle, and you have your normal force that the roller coaster tracks exert on the cart itself. At the top of the loop-to-loop, your normal force is acting in conjunction with the force of gravity. Now, regardless of the top or the bottom of the loop, the force of gravity and the normal force interact with one another in order to produce the centripetal force. In the case of the top of the loop, the force of gravity plus the normal force equals the centripetal force. At the bottom of the loop, the free body diagram looks different. At the bottom of the loop, you got your force of gravity, you got your normal force, and you got your centripetal force. Notice how at the bottom of the loop, the normal force and the force of gravity are not added together to produce the centripetal force. Rather, they are subtracted. And which one's always bigger? The normal force is at the bottom of the loop. Normal force is bigger at the bottom of the loop. You therefore kind of feel heavier than you really are at the bottom of that loop. Because that normal force, that roller coaster cart is pushing up on you pretty good in order to deliver that upward force and therefore that upward motion that you're about to experience going up that loop-to-loop. So assuming you're just going to make it, just barely going to make that loop-to-loop and not lose your footing at the top, because we know what's happening at the top. If your force of gravity wins, you don't stay in your circular pathway and you fall down. If the force centripetal wins, then you stay in that circular pathway and you don't fall down. So if you're just going to make it at the top of that loop, then that means that your normal force is essentially rendered null. And at the top of the loop, your force centripetal is equal to the force of gravity. Very similar to the car skid problem that we did earlier just a moment ago. Let's unpack this. Okay, m's on both sides of that equation, so they're rendered null, which might be a little weird because you're probably thinking, wait, the mass of the roller coaster cart doesn't matter? And the answer is no, it truly does not matter. What matters is how fast it's going at the top of the loop and how large the loop is, as far as us just barely making it through that loop-to-loop. And then from this point, once you figure out, let's say you figure out your velocity necessary to at the top of the loop-de-loop, to complete that loop-de-loop, you can use a variety of different techniques to figure out how fast you need to be going at the bottom of the loop-de-loop. For example, you could totally do kinematics, right? Because you have this distance here is given, and you know how fast you're now going up here. Solve for how fast you're traveling down here. You know, velocity initial or perhaps velocity final. The method I would use to figure out how fast I'm going at the bottom of the loop, though, mostly involves energy topics. I have an amount of gravitational potential energy and kinetic energy at the top of the loop-to-loop. I have, if I consider this ground, only kinetic energy at the bottom of the loop-to-loop. Therefore, if I figured out velocity using this equation over here, I can plug that into these energy equations and solve for velocity for this energy equation down here and figure out how fast I need to be going at the bottom of the loop-to-loop in order to complete the loop-to-loop. Finally, Unit 7 ends with a brief touch on Newton's universal law of gravitation. This refers to the law of gravity which exists between all particles and objects, well, I was about to say on Earth, but rather in existence. You need to be a cosmically large or astronomically large object in order to produce forces of gravity that are, measurable in a conventional sense. Let's say that we have a distance separating two objects. Whenever this is diagrammed or given as an equation, this value here means r, but it could very well be the distance between the two objects. Let's say we wanted to solve for the force of gravity between these two objects. The factors that matter are mass and the distance separating those two objects. Force of gravity is equal to constant capital G times mass 1 in kilograms times mass 2 in kilograms divided by the distance between those two objects squared. The constant is given as this: 6.67 times 10 to the negative 11 newtons times meters squared over kilograms. Questions that are asking about Newton's universal law of gravitation are usually pretty easy. You're probably given 3 of those variables and asked to solve for a fourth, or perhaps you're asked to do comparison values. We've doubled the distance, what happens to your force of gravity? Or one of those masses has been cut in half, what happens to your force of gravity? Or that sort of a thing.